Hey, welcome back. Are you ready? We still have this question here. Can we predict? Can we predict what? The value of one of the two variables knowing the other one. Is that appropriate? Come up to the top here. We've got linear regression in this case. And what we're still doing is trying to look at bivariate data which seems to follow a linear pattern. Okay, and fit that linear form to it. And regression, what does that mean? If you regress, you go back away from. And so what we're looking here is trying to fit a line, come up here to this top one and say, well, how much do these points regress or come back from the line? Can we fit a line so that we minimise the regression or the deviation away from that model of those points? And when we put in these lines to, here's one over here, come over here now, when we put that one in, that's going to be our predicting line. We could call that, in this case, L hat equals something times H for heat plus C. We could fit a line there. Well, this is our model. L hat is our predicted L value, predicted value of the length variable, in response or dependent upon the variable of heat. That's what we're going to be doing, and that little hat there, it means how well the model fits. And we've got one over here, we're going to talk about this later on. This is exciting stuff, where we are plotting a line which we call y hat equals A by X plus C. This is our predicted y value given a certain value in our variable X. And so is this appropriate to fit a line? And if we do, to describe the data, can we use it to predict realistically? Let's go and have a look at some maths associated with that. And here we are. It's called least squares regression. And we're going to investigate what that least squares means in a minute, but not just at the moment. Now, we've seen that correlation measures strength and direction between two quantitative variables, correlation. So we have looked and seen in some of these that the relationship appears to be linear. And we're going to try and now fit a straight line that best fits the trend in the data. Okay, the line of best fit, commonly said. And often in science you will do this by hand. Okay, and therefore trying to describe the linear relationship between the independent or explanatory and response variable. Please notice that in the IB syllabus they like you to use independent and dependent for the names of those variables. So we want a line of best fit. Is this a best fitting line? Or would you have put it more like that? How do you tell? We don't do it by line of sight. In mathematics, we are going to do it with what's called a least squares regression technique. So we'll have a look at that. We're not going to do it because that's outside the range of this particular course, but we're going to get technology to do it for us. But it's always good maths to see how it works, or try and understand how it works. Okay, so Pearson's over here says that obviously there is no straight line that contains all the points in the set. I don't think I agree with that one. Come on down and let's have a look at what we might say. Oh, here's a couple. I think you can see that if we have a correlation coefficient, Pearson's correlation coefficient, or product moment correlation coefficient, then if it's 1, our neg 1, the points do actually perfectly form a straight line. So that's the only case. That's pretty extraordinary that it would be like that. And as you come down with the correlation, you can see how well the line fits is a bit different as we come down. And I'm going to ask you here in these circled ones, is there any point in fitting a linear model or a straight line? Remember, a model is a mathematical description of some practical situation that's going on here. Is it appropriate Do they really, any of these follow really anything like a linear model? Question for you, how low would you go with your Pearson's correlation coefficient before it would become a bit silly to even suggest it's a linear model? Well, what do you think? 0.8? I'll give that a tick. 0.75, 0.7. Usually, if you have a look at the correlation when you have a correlation coefficient of 0.7, somewhere around the moderate, starting to be the moderate level upwards, remember R squared would be 0.49, it's only 50% of the variation in one would be attributable to the variation in the other. So think about that. I don't think you could have R less than about 0.7. So you might have a look at the plot, but I think you'll find that an R of about 0.7 gives you a fairly reasonable linear pattern there. But below that, hey, I think we've got to cross these out. Be a bit silly to suggest that was a linear model could be used to predict where the data points were. Are you getting the idea? What we're doing now is finishing it off, this question, can we predict, by talking about the strength. Now, the strength of this association, and can we now use it? All right, let's go on and have a look at some work on the calculator. Now, I've put only 22 of those data points in from the city consumption and highway consumption for the cars back before. And can you see, I've changed this around. I've changed this so that the X list is the city consumption, the Y list is the highway. Am I right? This is independent and this is dependent. Well, a student said to me, did it matter in that problem? I think we plotted it last time, or in Pearson's textbook, we had highway and city. Did it matter? Well, we can't say one is dependent upon the other, or one's explanatory, the other's response as such, so it can go either way. So the way I've got it, X list is city consumption, Y list is highway consumption. And do you remember, after you put those in those lists and set up your graph as a scatter graph, here it is here, and then you went to calc and hit F1, it gives you this window, and if you choose to fit a linear model, it's X. Now these are other models here, X squared, X cubed models, quartic, cubic models. Hit F2, we get this window, and I've chosen to fit a model in the conventional form, although often statistically they put it like this. I've chosen AX plus B, so Y equals AX plus B as the model, and up came this window. Now we chose this before to give us our R and our R squared. But look at what else they've got. Linear regression, they've got A and B values for the formula AX plus B. So, we could write in technology land the formula for this, because this time we've got this little pattern here. Let's go. This is city and this is highway, and it's a pretty tight model, pretty tight up here. But the calculator calls this X list, and this Y. So it comes with this formula, and I've plucked this number out, 1.228. There it is up there. There it is up there, and 1.452 as the values fitted by the calculator under what's called a linear regression model, least squares regression. We need to look at that in a minute and see what's going on. But now, this is very, very important in modelling, in mathematics. Here, do not use the technology symbols for the variable. X is the independent, Y is the dependent. We must contextualise it, bring it into the context. So the highway consumption is 1.228 times the city consumption plus 1.452. Do you get it? Now, do you believe that that is a reasonable predictor? So really, mathematically, this line should be Y hat equals 1.228 X plus 1.452. So this is the model. This is the predicted y for that set of x values. So in other words, if we plotted it, we would expect to put a line through there somewhere like that. And the rule is that line must contain the point x bar, y bar. As a result of the least squares regression, that point, the mean of the x's, the mean of the y's, will be on that line somewhere. Okay, let's check that out. Come down here, let's check that out. And to check that out, can you easily, with the calculator, having entered the data, can you find x bar, y bar? Do you know about this? Let's go back. Here's our first window over here, city and highway values, and then if we hit want calc, you hit F2 in there, and we get this window. This time there are two variables to be worked with. So there's 2 there. Hit F2, and we will come up with, oh well, hang on, no, I've messed that up now. Let's just get rid of that. We've got to set it first. So hit F6, and we just check it. 2 variable, x list 1, y list 2, check that, then exit that screen, and we come here. Now we're ready to examine the 2 var statistics, which is hit F2, because we've set it up, and the first window starts off with x bar and all that, as usual. If you scroll down with F6 or the button here, then you will get this window over here, and there's y bar, or all the values you want about the y variable, the mean, standard deviation, all that. We're not going to use that in this course. So here we are. We have the mean of the x's taken separately and the mean of the y's. Now with the least squares regression method that technology uses, and we don't have to do it ourselves in this course, part of the result is that the mean, or the point with the mean of x as its x-coordinate, the mean of y as its y-coordinate, will lie on the line. Let's check it out. Come down here and let's have a look. I put it in. Here's our model. We say that h is approximately 1.228c plus 1.452. It's our model, or our predicted h, if you like. Okay, let's put the means in. Here's the mean for x. That's for the city value. And here we add on the 1.452, and what do we get? Yes, the y is approximately equal to the y bar, or the h bar, if you like, in context there. So you can check the mean, that the mean of the point with the mean x and the mean y as x coordinate and y coordinate does obey that predicting line. This is the predicted model. And it's only predicted because not all the points lie on it. Now it's a line of best fit, we say here. This is a line of best fit under a regression model. Line of best fit using least squares regression. Okay, let's do some more. Come down and have a look at this one now. How do they do least squares regression? Well, to fit this line under least squares regression, the process is this. You want a green line there which minimises the sum of the deviations of the points away from the line. So these little blue squiggles I'm putting here show you that some data points are away from the line. Now we want to minimise the total deviations. Minimise the total deviations of points, each point away from the line. Now you can see, can we just add them up, sum the deviations? No, because the sum of the deviations could be approximately 0. This one would balance out that one. That one would balance out that one. So how are we going to have a process which positions a line so we minimise the total deviations? Well, do you remember compare with the sigma formula? What was that? The square root of the sum of fi xi minus mu squared on n, averaging the squares of the deviations away from the mean. Why? For the same reason. We didn't want to, due to the symmetry of the distribution, cancel them all out. We squared and added them. So that's where, up here, least squares regression comes from. If we try to find directly the minimum deviations, they could all balance out, some above, some below. So we square them, square the deviations away from the line, and then minimise that sum of squares. And that then will give us our least squares regression line. Okay. Now, the mathematics of that is quite complicated, and Pearson's got a good treatment of that, so you might like to look at it in that textbook, a very good explanation and showing you how it's all working out. But in this course, we only have to use technology to actually fit that line. So this is our predicted line. If you like, y hat equals ax plus b, or sometimes they put it the other way, y hat equals a plus bx. Not the same a and b, of course, just a different form to put in, whether it's sort of slope by x value plus intercept or the other way around. All right, are you getting the hang of it? This is how it's done to fit our line of best fit, not by line of sight, mathematically now. Okay, so let's have a look. Here we have, going back to the calculator, I've clipped the two windows, this time with the line drawn. So if you get to this window and you hit draw, then it will draw the graph with our line in it back over here, and we'll get that window, just to see how well it fits. And this copy means you can actually hit that and copy that formula back to function mode and draw the graph of that if you wanted to. All right, okay, in function mode. Okay, so let's have a look. Is this a good fit? Is this a good predictor? Remember here, this is really y hat here, a prediction of the y value according to a least squares model, minimising the squares of the deviations away from this line. And this is the best line. It's got the least value of the squares of the deviations or regressions. All right, remember I said regression? Okay, how much it pulls back? So it's a least squares regression to minimise how much the points regress from the line. Okay, how much do they? Let's go over and see what we think. It's got a very high R and R squared, and this is a good fit. Pretty good, isn't it? Number of points right on the line in here, and look at the others. There's a random variation of the other points around the line, as you'd be expecting for a line of best fit under least squares. The process minimises the sum of the squares of the deviations away from the line. That's the idea, basic idea. So this is random variation of the other points around your model, other points. So you'd expect that. This sort of traps a model. It's not going to go too far away from those because it's a least squares regression model. We can't have that the points regressing too much from our model. Okay, so here it is. Back in the context, highway consumption and city consumption. What does it mean now? Let's see if we can unpack the meaning of this particular model. As C, now this is important in this course, as C increases by 1, right, what happens now if C increases by 1? So as C increases by 1, what's going to happen? Well, let's have a look. We've got 1.228 times C. So that means H will increase by 1.228. So in any of this modelling, it's important to be able to say that. We would say, this is the slope, isn't it? AX plus B, or the old Y equals MX plus C, Y-intercept, and the slope. Do those things have any meaning in this modelling? Well, the slope does, because it's the amount, let's just check it here, it's the amount the dependent variable changes for the independent variable. So as we go up there, it is the H step, or change in H, over change in C. So one movement along here in C, 1 unit, will have, if it's a slope 1.228, it's got that C movement. Delta H movement, so the H movement. So the change in the independent variable is 1. The slope will be the ratio of that value to 1. So what does that mean? Well, can we write it in words now? Well, something like this. For each 1 kilometre per litre change in city consumption, we expect what? A 1.228 kilometre per litre change in the highway consumption. Now that's a standard interpretation of a slope of a line, any line or linear model like that, and it's because the slope of the line, the number in front of that other variable when we put it in this form, is the ratio of the change in the dependent variable to the change in the independent. So if you make over here that 1, 1, this is going to be the other number. So it's always going to be true. Okay, so you can genericise this. Oh, that's ardyism. You can make this a generic statement. If you change the independent variable by 1, then the dependent variable will change by whatever the slope is. Okay, and don't forget the units. This is in context. This is modelling now. We're trying to actually apply our mathematics to a practical situation called modelling. All right, do you get it? How are you going? What about coming down and having a look at some further developments here? Exceptional case of the regression line. If R is naught, the regression line is horizontal, its slope is 0. I don't think there would be a regression line, would there? Here is R is 0.2. R is 0 would be just perfectly flat. Why would you put a line through it? No. It doesn't predict anything. There is no linear relationship there, association. And we said R was what? Approximately, well, hang on, let me put it like this. Greater than 0.7, approximately. Okay, you can go by a bit of visuals there. If R is 1 or neg1, the line is perfect. The model, the y hat, is perfectly equal to the values of y. It's a perfect fit. And as one goes up, here it is, the other goes up. And with a negative, as one goes up, the other one's coming down. But it's a perfect correlation. So the line of best fit is a perfect model. All points for these two, all points lie on the line. Okay, there's no regression away from it. Okay. All right, so get that idea. It's not always going to be appropriate to fit a line at all because the correlation coefficient is so small that it suggests there's too much deviation away from that model, from that line. Let's have a look. Come back to our question. We're going to finally try to answer this. Can we predict? Okay, so let's put some provisos in. All right, number one, if R is sufficiently close to 1, and this is a matter of opinion, then what will we do? We fit a least squares regression line. Right, we fit that, so here we are, somewhere through there, remembering that on that line, x bar, y bar, that point will be on the line under the process of the model. Now, what can we do? Can we predict? Well, let's say that was true, so they were fairly closely associated, which is this set of data here. We've fitted a line. Now what are we going to do with it? Can we use it to predict anything, even if they're tightly associated and we've got a pretty good model there? Well, the first thing that we don't want to do, as we saw with the car data here, we took away the outlier. We don't know what happens as we go further out. That is questionable. Now that's called extrapolation. Come over here to Pearson's. Extrapolation, extra points. Polation comes from points, extra, outside. So these points are outside the range of data. The modelled range. Okay, we set our model up from here to here. Now, there's no reason to think that the pattern that produced that model will continue on. So, what about saying, that's called extrapolation. Extrapolation is, here it is, extrapolation is extremely suspect. Right? Because there's no reason to believe that the relationship is going to be the same as we go on. Things change. Highway motoring, engines heat up or whatever, various things change that aren't obvious in this range here, up to 12 kilometres per litre. A car doing more than that may not do more than that in city motoring or in the same correlation or the same association or according to the same model. Different things are applying. Perhaps, we don't know. So we say we cannot extrapolate reliably. So I'm going to put that down here. Extrapolation is unreliable. Generally. That will be our general statement there. What about the other one? What about interpolation, interstate, between states? Okay, what does it mean, interpolation? It means between points. If we tried, for example, to predict what a car doing 9 kilometres per litre on the highway would do, is that reasonable? Yes, well, it's within the data set. The model was deliberately constructed to describe points in that region. So if one is between all those points, we would say interpolation is generally reliable. Generally reliable. Now, with a couple of provisos, the provisos up above, and that is, was there a good correlation? Was up the top here, was R sufficiently close to 1? Okay, not much sense in fitting a regression line and trying to use it to model or to predict within a range if there wasn't a close association. Okay, so over here from Pearson's, interpolation is sometimes reasonable when the scatter plot shows a strong relationship. And there we would say probably R greater than 0.5. And the other thing is we've got a good point here which we just discussed before, and that is the data points generally, if R is high, will be close to the line and randomly distributed, some above, some below. Just to check that a linear model is appropriate. Sometimes you can get high R's here, and R-squared values, and really a better model might be a curve. So we're going to say we will observe the distribution of points around that model, okay, and see that some are above, some below, random distribution around it, so it's trapping the model between them, and a number of points lie on or close to the line. So we use a bit of common sense there as well. Okay, don't go blindly away and let the calculator fit a least squares regression line to any set of data. Look at the data. Is the linear form appropriate? Does the R support that? Does the set of points support that in their distribution around the line? That's important. Okay, let's go on now and have a look at some problems. Okay, so these are again from Pearson's. You can check the textbook there, be a good idea. And the first question in 4B is to describe or develop a regression model for each question in exercise 9.4a and interpret the slope of each. So I've extracted the data from 9.4a. Okay, so you might just check that from the book. One was just X and Y. X is independent, Y is dependent. Here, speed and fuel consumption. Speed was independent, fuel consumption dependent. And just a note there, if we do that, put speed here, we say the way we describe that, and we put that in kilometres per hour, and this is fuel consumption in kilometres per litre, with our scales on there. We say fuel consumption versus or against speed. That's the way we say it mathematically. Rather than drawing it, we could say fuel consumption will be plotted against speed, or fuel consumption versus speed. So that one comes after the word against, is the independent variable. Okay. Let's have a look down here, country, and our two values here, GNI, gross national, well, I've forgotten what that is now, per capita, and I'm not sure what they measured, have to go back and read that, but this was the independent variable and this was the dependent variable. So we need to get a regression line for that by putting that into X list and Y list. Have a look back at 9A to see what those two were. Visitors, number of visitors, independent variable, and how the consumption of electricity increased. So Pearson's have actually got them into independent and dependent variable data there for you, and then you just go into the calculator for a regression model. Okay, so have a go at those. And pause the presentation and get the data down there. Okay, let's have a look at question 2 here. A fair bit of data, so I'll scroll down. So I want you to read that now and pause it, and then I'll show you the whole data set now, which is, I think it all fits on the screen. I try to fit it here pretty much. Yep, all fits on the screen. So the first 20 students there, and the two scores before and after. I've forgotten what that is now. Let's just go up here a little bit. Yeah, before and after. So put those into list 1, list 2. What would you say? Before as independent and after as dependent? Possibly. Not so fussy here in terms of that, but probably that would be the best. Let's have a look at question 3. Okay, so there's your data. Need to actually put that into list 1 and list 2. Here, independent and dependent. And here's what they want you to do with it in question 3. Okay, going on to question 4. Let's have a look at what that's got to offer us here. Some marks there. Don't know about independent and dependent. I would say probably physics, being a mathematics man myself. The physics performance will be dependent upon the mathematics. You must have mathematics skills in all the sciences. Okay, let's go to question 5 now. That's question 5. Okay, so let's have a look at the answers now and see what we got. Check these with the yellow marks and things on it. Did you get those formulae? Could you please notice that Pearson's have put the formula the other way around? So what that would mean is y equals still the same number in front of x, is still the slope, plus 3.58. It doesn't matter, does it? You'll have it the other way around. Generally in the formula you don't put the units. I would prefer people putting fuel consumption equals 0.116 speed plus 24.1. Just watch the units here, because some of them are in thousands and things. Just check that you agree with the answers there. Okay, let's go down. Question 2. Okay, let's see the rest of that in a minute. Yep, there we have the rest of it. Okay. Come down then to question 3. A bit more of question 3 coming up in a minute. Don't know what this blue mark is. 47,100 euros. Better check that, because this is 1,000 units. For every increase of 1,000 units in production, the cost on average will be increased by that. I think 1 unit here was 1,000. I think that's what they're getting at there. Okay, I want to check that. We'll have a look at that later. Let's go down D of that, part D. So yes, check this one here. Have to go back to the question. Have a look at the 1,000 units. I think that might have only been effectively 1. They were already in thousands. Don't know. Yeah. Okay. Let's come down then to question 4. Here, having a look at the R value, would you really use a regression line to describe the linear association? A bit weak to even bother, wouldn't you? I think you might say. Okay, so there we have it. Here's question 5. Question 5. Bit tenuous, this one. I don't know what the R is. 0.93. Bit of a problem with some points here. Want to have a look at the line of best fit. Appears to be. It's surprising to have such a high R there with the way this looks. Positively sloped trend. Positive correlation as points increase, so the price tends to increase. Okay, so might just take the point here that the y-intercept, which is the value down the end here, if you have none of the other value, is it appropriate to have a price at all? And the answer is no, it's meaningless. We might look at the interpretation of those lines. Okay, how did you go? Are you getting the hang of it? Very important to understand with this bivariate data that it is useful to be able to predict things, only if it's appropriate though. It may not always be appropriate, need that high R and get a reasonable line that appears to be a good fit, good distribution of points around it. Okay, well that finishes this section of the descriptive statistics in the IB course now. We'll move on to probability and some inferential statistics later on. I hope to catch you then. Cheers for now.